Hello, everyone, and welcome to this new appointment of the 40 Under 40 lecture series on combustion. It is my great pleasure to welcome Professor Cho for the lecture today. He's an assistant professor at the University of Texas at El Paso, Aerospace and Mechanical Engineering Department. He received his Bachelor of Science in Mechanical and Aerospace Engineering in 2014, and a PhD in Mechanical Engineering in 2020 at the Seoul National University, where he conducted experimental kinetic studies. He actually had two postdoctoral appointments, the first in Argonne National Laboratory and the second in the National Renewable Energy Laboratory, where he actually delved into theoretical kinetics and machine learning techniques to predict combustion characteristics of renewable fuels. His studies combine a solid background in experimental and theoretical kinetics with the objective of designing sustainable and high-performance polymeric materials. Today, we talk about accelerating the discovery of novel fuels and material through AI theory experiments integration. I look forward very much to this talk, and I give you the floor. Thank you again for having accepted our invitation.
Sure. Thank you for introductions. Again, this is Jaeyoung Cho. I'm an assistant professor from the University of Texas at El Paso. Well, I'm really glad to be invited to this seminar series of the 40 Under 40 e-lecture series on the combustions. Today's presentation that I prepared is about my previous researches and ongoing researches that I've been doing for accelerating the field and material innovations through the AI theory and experimental studies. I would say it's like almost like 12 years of experience in the research field. I was fortunate enough to have a balanced experience in the AI technologies and theoretical kinetics and experimentations. So these days, as an independent researcher, I was trying to combine this solid background in AI theory and experimentations for accelerating the biofuel discovery and the polymeric binder discovery for the manufacturing applications. So, though this community is basically a combustion community meeting, but still, I think it is not a bad idea for starting the presentations with the basic concept of the biofuel, because there can be some undergraduate and graduate students which is comparatively new to this field. You may know that the biofuel is kind of the promising alternative for the medium to heavy duty vehicle, for decarbonizing the medium to heavy duty vehicles. The biofuel can be synthesized from the biomass through the thermochemical processes. And once you synthesize these biofuels, you can distribute this biofuel to the transportation system like an airplane and the trucks and a boat to the gas stations. But when it burns, it generates CO2, of course. However, the CO2 can be absorbed by the biomass through the photosynthesis process. So we call this biofuel have a lower carbon footprint compared to petroleum-based fuels. If you look at the figure on the right side, you will see that the greenhouse gas emissions from the life cycle of the bioethanol. Let me see if I can use my pointer quickly. Right here. You will see that the bioethanol have a 43% lower the greenhouse gas emissions from its life cycle, which is kind of remarkable. But one of the beauties of the bioethanol is coming from is the feasibility of the carbon capture and storage system, which is called the CCS system. One of the dominant source of the CO2 emissions from the ethanol production is coming from the fertilization of the starch. And when you're fertilizing this starch, you're gonna make some CO2 coming out of the bioethanol refinery. However, the CO2 has a very high concentrations of around 80% to the 90%. So it is comparatively easier to capture this CO2 to the high purity and store into the designated facility. So this feasibility of the CCS technology for the bioethanol made it more promising as an alternative source of the powertrain energies. So if you take into account this feasibility of the CCS technologies, now you will see that the overall emissions from the bioethanol can be the negative, which means that as you're burning the bioethanol, actually you're absorbing the more CO2 from the atmospheres. But still, the bioethanol is not a single choice of the biofuels. There can be multiple choices for biofuels like DME, dimethyl ether, can be one of the good source of the compression ignition engines, with diethyl ether, or the biobutanol can be another source of the biofuels. So for the entire of my research career, I have been trying to answer to these questions shown in this slide. I was asking like, which molecules are the best alternative to fossil fuels to achieve sustainable proportions with high efficiency and a low environmental impact? I believe these questions can be answered through the 3 different steps of the research. First of all, I believe the first thing that we have to do is the massive screening of the organic molecules. You may think of that they're almost like an infinite kinds of the molecules out there in the universe, but not all of them can become the fuels in a powertrain. For example, some of the molecule may have a too high boiling point, or some of the molecule have too low reactivity. So the first thing that you have to do is to find out which organic molecule can become fuels, while which molecule cannot become a fuels. Now, after selecting some 2,000s or the 3,000s candidates of the molecules, then the next step that you have to do is to down select the fuel candidates. This is where you have to understand which fuel is cleaner, which fuel has a higher performance in the propulsion systems. So at the end of the day, after the down selection of the fuel candidates, you're going to have only a few fuel candidates like a 3 to 5s. Then it's time to evaluate the performance of the fuel candidates in the propulsion relevant conditions. As I mentioned earlier, my research career has been about from the top to the bottom of designing the biofuel for the propulsion systems. The first step, massive screening of the organic molecules. I have been utilizing machine learning technology for rapid screening of the molecules that can become fuels for the powertrain systems. One of the beauties of the machine learning technology is that it provides us the predicted value of the fuel properties of the molecules within a few milliseconds. So it is fast enough so we can utilize this AI technologies for massive screening of the organic molecules over than 1 million molecules. And the second step for the down selection of the fuel candidates, I have been utilizing theoretical kinetics and the combustion simulation like DFT calculations and molecular dynamics simulations for further narrowing down the fuels that have a cleaner emission characteristics and a higher propulsion performance at the aerospace propulsion systems. And once I find out the final fuel candidates, I had to move on to the lab scale experiment to measure their combustion characteristics. And I have been a big fan of the kinetic devices like a rapid compression machine. And now we're going to introduce you the details of the research area from now on, starting from the machine learning technologies for the massive screening of the organic molecules. So graph neural networks. Graph neural networks is one of the machine learning technologies that has been popular choices for molecule design. Graph neural networks, GNN, converts the molecular structure into the 2-dimensional graphical structures, where the atom is represented by the nose and bones is represented by the edges. And the graph neural network, GNN, is known to excel in predicting the physical chemical property of the molecules. This is why the GNN has been popular choices for the fuel designs. So let me give you some example of how the GNN works. Let's say I want to predict the fuel property of the 2,5-dimethylfurans, that you're going to have some 2-dimensional structure of these molecules. Then this molecular structure can be converted into the 2-dimensional graph. As you can see that the atoms was converted into the nose and the bones were converted into the edges. Then all the descriptive informations about the atoms and the bones can be stored in each nose and edges. Like this atom number 7 is oxygen, and this atom number 7 does not have any hydrogen attached, and this atom is in a 5-membered rings. Similarly, this bond F is a single bond and a CO bond, and this bond is in a 5-membered rings. Now, all these descriptive informations, which is written in English, not in numeric vectors, can be converted into numeric vector with a fixed size, let's say like a 64:1, by using the feature embedding layers. So once you get these numeric vectors for each atoms and the bones, these atom features and the bone feature can be updated over and over again through the hidden layer, which is called the message passing layers. And at the end of the models, you're going to get a predicted fuel property that you trained earlier. So this fuel property can be anything depending on what you trained earlier. This can be like a boiling point or critical point of the heat of vaporizations, or some combustion characteristics like a C10 number or the Sooting index. So this diagram shows you some more detailed descriptions about the GNN model that I was using. But the purpose of this presentation is not about explaining details of this AI model. So the thing that I wanted to tell you from this slide is I had to divide the input features of the GNN model into the atom features and the bond features. And these atom features was stored in on a nose, and the bond feature was stored in the edges. After the embedding layers, all this descriptive information is converted into the numeric vectors, and these numeric vectors went through the 6 times of the message passing block. And this 6 times of the message passing block, in this message passing block, these atom features and the bond features are interacting each other, so that we can take into account how the bonds are affecting the atoms characteristics and how the atoms characteristics are affecting the bonds characteristics. Now, after repeating the message passing block the 6 times, we're gonna take this atom features to the dense layer one more time to reduce the dimension to the 1 by 1, and then we're gonna get the final predicted value of the fuel properties. So again, the key of this presentation is about how we were gonna utilize this GNN architectures for a biofuel design. So when I was a postdoctoral researcher in the National Renewable Energy Laboratory, one of my research goal was to train GNN model the fuel properties. This fuel property can be like a C10 number, which represent the reactivity of the molecules, or the Sooting index, which is related to the particulate matter emission characteristics of the molecules. But it may sound like comparably easier, but there is a huge challenge of training the GNN on the fuel property. That is, there's only limited number of the fuel property database. Let's say, for example, for the C10 number, there's only 600 database for the C10 numbers. You may think of the 600 database maybe kind of massive database, but in the perspective of the AI, we cannot say this 600 as a big data. So because of this limited database of the fuel property, you always have to compensate the accuracy of the AI, which is kind of big challenges for the AI model. So all of my research career for the AI predictions and fuel property was about how to overcome this limited number of the fuel property and make some reliable AI models. So I can summarize my AI researches for the fuel property prediction into the 2 different categories. For improving the AI technologies with a limited database, I have been utilizing 2 different approaches. First approach was to evaluate the data quality. In other words, I put a more weighting on the reliable data when I trained the GNN model on the fuel properties. For example, from the 600 database for the C10 number, about 60 to 70% out of them was measured from the standardized constant volume combustion chambers like IQT or the AFIDA or the CFR ranges. So this standardized method was verified by the ASTM. So the amount of validations and amount of uncertainty that we have for this database from the ASTM certified devices, we can consider it to be kind of reliable. But the remaining like the 20 to 30% of the database was coming from some the in-house constant volume combustion chamber, which was developed by the individual institutions. This individual constant volume combustion chamber may have some high reliability for certain applications, but the amount of validation that we conducted for such an individual constant chamber and amount of the uncertainty evaluations for these devices is not as much as those of the IQT and AFIDA and the CFR ranges. So what I would consider is the C10 number measured from the individual constant volume combustion chamber may have a lower accuracy compared to those of the AFIDA and the IQT and the CFR ranges. So based on these knowledges, I had to divide the C10 number database into the 3 different categories. The first category is the tier 1, which is a high quality, and tier 2 and the tier 3 is comparably has a lower quality in accuracies. After dividing the data into the 3 different categories, I put a different weighting depending on the tier of the data. let's say I put a more higher rating on a tier 1 data when I'm training the GNN model upon the Sooting numbers. So even though it sounds like very simple approaches, but just by dividing the database and putting a different rating, you can get like a 20 or 30% improvement of the accuracy of the AI, which is quite impressive with a given number of the database of the Sooting number. The another approaches that I like to use for improving the accuracy of the model is to utilize the transfer learning technologies. These transfer learning technologies can be interpreted as the getting a hint from the another GNN models. Even though we only have a 600 database for the Sooting numbers, we already know that the Sooting number is kind of related to the heat of vaporization of the fuels, because Sooting number is measured at the spray combustion environment, and the spray combustion occurs it occurs through the vaporization of the liquid fuels and the cooling of the ambient temperatures through the heat of vaporizations and a physical mixing between the vaporized fuel with the oxygens and autoignition at a certain point. So this is what happens in a CFR range in a AFIDA and IQT devices that measures the Sooting numbers. So inherently, the Sooting number measurement supposed to be sensitive to the heat of vaporization of the fuel because it determines the ambient temperature of the testing. So we try to leverage this physical knowledges by developing the additional GNN model that predict the heat of vaporizations. The good thing of this heat of vaporization is we have a very massive database. We have more than 100,000 database for the heat of vaporizations. So once we train this model on the heat of vaporizations, I was able to utilize the output of the GNN model from the HOV to better predict the Sooting number using a GNN models. We call this process, even though I just simplified this architecture of the transfer learning technologies, these transfer learning technologies can overcome the limited database of the Sooting number based on the physics that we know. So these two technology has been a major strategy for me to improve the accuracy of the AI model with the given amount of the database. And this is one example of the GNN model's accuracy for the Sooting number. Here, the y-axis is measure the Sooting number from the experimental study, and the x-axis is predicted the Sooting number, and each dotting diagram represent the individual molecule within the database. So you will expect that there is a 600 database in this diagram. If you look at this mean absolute error of our Sooting number prediction model, then you will see that the accuracy of this model is around 2.44, which was one of the highest among the literature at the moment of publications. This mean absolute value of the Sooting number prediction model that we developed had a very similar uncertainty bound with those of the experimental data. That means the AI technologies that we developed for the Sooting number were in the level of replacing the experimental data if the molecules that we are interested in it can be interpreted as an interpolation of the database. So we were really happy for seeing the success of the Sooting number prediction model. So we were eager to move on to the other fuel properties so we can utilize this AI technologies for further screening the biofuel candidates. So we literally tested this AI architecture for the other fuel property, including boiling point and a flash point. The flash point is kind of property related to the flammability of the molecules. And here we can see that we tested the boiling point and a flash point of like a 2,000 saturated alkene molecules, and each dot represent the single molecular structures. So there's like a 2,000 dot here. And all these boiling point and flash point value was based on our GNN models that we developed as a part of the green chemistry publications. And depending on the boiling point and the flash point of the molecules, we can categorize the molecule into diesel range and a jet fuel range and a gasoline range. And we were particularly interested in those in a jet fuel range because we are about to design a novel molecular structure for the sustainable aviation fuels. So we took the molecule within the jet fuel range into the second screening process based on the Sooting number and the yield Sooting index. As you know, Sooting number is the reactivity of the fuel, and the yield Sooting index is kind of indicator of how many the soot is being emitted from the molecules, and of course, lower the better. We fortunately had an additional in-house model for predicting the C10 number in an Sooting index of the molecules. And based on this prediction model, we are able to screen further the molecule based on the emission characteristics and the reactivity of the molecules. So we are able to recognize 20 to 30 molecules satisfy all the stringent regulations on C10 number in the Sooting index and a flash point and a boiling point. It is kind of remarkable progress because we started from the 2,000 molecules in the beginning, but we ended up to have a 20 to 30 molecules at the end of the day. This is some example of the molecules that we recognize at the end of the screening process. So this initial screening process based on the AI technologies reduces the fewer candidates that we have to think of in the following stage of the research is using a theoretical kinetics and experimentations. That is, by using these AI technologies, we don't have to test all the molecule out there. We can just concentrate our effort in a few molecules that can become a fears in the futures. So this is one of the beauty of the AI technologies in the biofuel design. So there was my brief introductions about my experience in machine learning technologies. Then I'm going to move on to the second screening process, which utilize the theoretical kinetics and the combustion simulations. Pardon me. After a couple of years of experience in machine learning technologies, we realized that ether fuels are quite good. The ether fuels are the molecule that contains oxygen atom in the middle of the carbon chain, and the ethers are easily synthesizable from the biomass and generate less particulate matter like a soup particle. And one of the beauty of the ether fuels are the C10 number of the ether fuels are sensitive to the molecular structure of the ethers. Here I prepared the bar graph that shows you the C10 number of various ether molecules spanning from the linear ethers, branched ethers, and cyclic ethers like oxetane, oxalane, and a dioxalane, and an oxane. You will see that the C10 number of this ether molecule spans from the 9.9 to the 111.0s. So this variety of the C10 number gave us a lot of freedom in designing of fuels. Sometimes you can use the ether for the gasoline engines, which requires low reactivity, or sometimes you can use the ether fuel for the compression ignition engine that requires high reactivity of the fuels. So this flexibility of the C10 number to the molecular structure made this molecular class to be of interest to the fuel designer. However, there were still very limited understanding about the structure property relationship of ether fuel C10 number. So if you don't know about a structure property relationship of the ether C10 number, you cannot maximize the utility of the ether number depending on your applications. So we try to provide some fundamental researches on the structure property relationship of the ether C10 number by using the flow reactor in a FIDA experiment. So for the fundamental study, we selected 5 representative ether molecules with varying molecular structures spanning from the linear, branched, and the cyclic structures. And we named each molecule based on their molecular features and the number of carbon atoms and oxygen atoms. Like this first molecule is linear C1001, second one is branched C1101, and third and fourth and fifth is cyclic C802, cyclic C602, cyclic C501. And then we measure the C10 number of these molecules based on the FIDA measurement. Unfortunately, we were able to see that a very huge variance in the C10 number among these 5 molecules. The linear C1001 has a 111.0, cyclic C501 has a C10 number of 9.9. So we wanted to further understand why some of the fuel have a high reactivity while the other has a low reactivity. So we put them into the flow reactor. So if ether fuels and oxygen and helium was provided into the heated flow reactor, and then we measured the chemical spaces coming out of the flow reactor using a gas chromatography and a mass spectrometry. So this is one example of the flow reactor results from the linear C1001. Here the x-axis is temperature and the y-axis is carbon yields. I know it is kind of unconventional way for representing the product concentration, because usually the product concentration is represented by the mole fraction of the chemicals. But here in this study, we use the carbon yields. So we can understand where the carbon is going. We wanted to understand the molecular flux into the chemical products. So if you look at this flow reactor result for the linear C1001, you will see that in the low temperature, so you cannot observe any oxidation feature from the linear C1001. But as you go above the 500 Kelvin, you will see some evidence of the oxidation of this molecule, making a lot of oxidation products out of it. So this is what it is for the linear C1001. Then let me compare this result to branched C1101. This is flow reactor results from the branched C1101. You will see that the overall behaviors are similar, where the branched C1101 have a clear indication of the oxidation around 400 Kelvin to 500 Kelvin. But when you compare these two graphs, you will see that the amount of oxidations that occurs in a branched C1101 is much smaller than the C1001, which indicates that the oxidations reaction of the branched C1101 is much lower. It is much lower than those of the linear C1001, and it is consistent with lower C10 number of the branched C1101 compared to the linear C1001, which has a higher C10 numbers. Then you were going to be curious about the flow reactor results for the cyclic ether molecules. Interestingly, we could not find any evidence of the oxidations from the cyclic ether experiment. You will see that none of the oxidation products occurs, and the concentration of the cyclic ether molecules were the same across all the temperatures. So it is consistent, again, with the low C10 number of the cyclic ethers compared to the acyclic ether that has a much higher C10 numbers. So I was fortunate enough to find out the consistent result between the C10 number measurement and the flow reactor measurement. And this consistency between the C10 number and the flow reactor may indicate that the C10 number is related to the oxidation kinetics at 400 to the 700 Kelvin. It may be kind of obvious to some of the scientists and engineers in the combustion community, but at this moment, we were happy to find experimental evidence that verify that the C10 number is actually related to the oxidation kinetics. So we moved on further because now we know that the C10 numbers are related to the oxidation kinetics. We moved on to understand how this oxidation occurs in this low temperature bound. This is the reaction pathway at the low temperature that many people already know. Let me briefly introduce about this reaction pathway. Let's say the fuels RH, they experience the hydrogen extraction reactions through the hydroxy radical and make some alkyl radical. And this alkyl radical we combine with O2 make a ROO, and this ROO isomerizes to the QOOH. And once you make a QOOH, this we combine with the O2 again, making O2QOOH. This O2QOOH dissociates further to the keto hydroperoxide and a keto alkoxy radical that makes two additional hydroxy radical that come back to the initial fuels to accelerate the combustion reactions. Again, this reaction pathway is already well known for most of the fuels, but what I wanted to do was to calculate the potential energy surface along this low temperature chemistry. This is potential energy surface of the low temperature chemistry for the linear C1001. You will see that the energy going up and down, and this energy was calculated from the G4 composite method, which is kind of the DFT and the Hartree-Fock composite method with the uncertainty bound of the 1 kmol, which is kind of the accuracy, which is kind of accurate. You will see that the energy going up and down during the low temperature chemistry, but what you have to focus on this diagram is there is two energy barriers between ROO and a QOOH, and an OOQOOH and a keto hydroperoxide. Again, this is not new to the community, but they already know. But now, what I wanted to tell you from this diagram is actually when you change the molecular structure of the ether, the energy barrier changes a lot. Here you see that when you are calculating the energy barriers of the acyclic ethers like linear ether or the linear ether and the branched ether, the energy barriers of the isomerization is around 20 kmol. However, once you have a cyclic structure within the molecules, the energy barriers increases a lot. Sometimes it goes up to like a 40 kmol. And these higher energy barriers of the cyclic ether is consistent with what we observed in the flow reactor and the C10 number. That is, cyclic ethers has a higher energy barriers, and that leads to the minimal amount of the oxidation reaction in a flow reactor, and it is related to the lower Sooting number of the cyclic ethers. So this theoretical study tells us a lot of things about the designing of fuels. If you want to have a low reactivity fuels, you may low reactivity fuel, you better use some cyclic ether because it has a higher energy barriers of the low temperature oxidations. But if you want to have a high reactivity for fuels for the diesel engines or the jet propulsion engines, you better use the acyclic ethers so you can lower the energy barriers of the low temperature oxidations. Again, it may not be very new to the scientific community, but this was the first time to systematically validate that the Sooting number of the ether molecules are quite tightly related to the energy barriers of the low temperature chemistry. So there was the example of how I utilized this theoretical and experimental capability for understanding the structure-property relationship of the ether as a Sooting number. Recently, we moved on to utilize the same capability of the DFT calculations to evaluate the molecule's Sooting tendency. This reaction pathway was presented in the last combustion symposium in Berlin. In the last symposium, we presented a very interesting dependency of the Sooting index to the positional isomerisms around the single aromatic molecules. If you look at this vanillin molecule, you will see that the YSI value, which is indicator of the Sooting tendency, is around 47.7. But by just replacing these formula groups into the near the hydroxide groups, then you're going to make all vanillin. Then the YSI value increases to the 69.7 by the 22 unit. So what you did is just replacing the formula group from the para to the ortho positions, but you ended up with having a much higher Sooting tendency, which was kind of interesting to us. Another thing that you can find out from this diagram is once you move away this methoxy group from this hydroxy group to the meta positions, then you were going to see that this YSI value slightly decreases by the 5 unit. And if you move away further, then you're going to see that the YSI value becomes much smaller than the all vanillins. So comparing these 4 different molecules' Sooting tendency tell you that how sensitive the Sooting tendency is to the positional isomerisms of the single aromatic molecules. So we try to explain this dependency of the Sooting tendency to the positional isomerisms. We successfully explained that it is related to the energy barriers to forming strong precursors like cyclopentadienyl radicals. In other words, the all vanillin turned out to have a lower energy barriers to form the cyclopentadienyl radical, while the other molecules have a higher energy barriers to form a strong precursors. So this is another example of how we can utilize this theoretical capability for further refining the biofuels molecular structures. By comparing the energy barriers to strong precursor, we can explain what kind of fuels may have a higher Sooting tendency, what kind of fuel have a lower Sooting tendency before we are testing it. So another beauty of the theoretical study is that obviously, maybe all of you guys may know it, the theoretical study is to develop some detailed kinetics mechanism for the flame simulation and the CFD simulations. My job in the Argonne National Laboratory was entirely about building a potential energy surface for the radical dissociations and utilize that potential energy surface for calculating the rate coefficients using a microcanonical transition state theory, and then update the detailed kinetic models and simulate the influence of the novel theoretical rate coefficients for the flame simulations. That was my occupations in the Argonne National Laboratory. So this is another example of how to utilize theoretical approaches for the screening out the biofuels. The theoretical approaches give us some ability for explore the various molecular structures with the quantum mechanics calculations, and depending on what molecules you are studying, you can construct the additional the module of the combustion mechanisms, so you can simulate another molecule within the Cantera and a Cankin environment. So combining with the other example of the Seaton number predictions and YSI predictions, and this is another example of how theoretical calculation can help us to refining the molecular structures of the biofuels before we are moving on to the experimentation stage. So there was some detailed descriptions about my theoretical capability, and then I moved on to the final steps for validating the influence of the final fuel candidates in a propulsion environment. Well, right. This was a story that I had in South Korea. I was born and raised in South Korea. I took all of my degree from the Seoul National University in Korea. I was participating one of the biggest projects within the Korea is about decarbonizing the light-duty vehicles using a bio-alcohol blended fuels. So South Korea government was interested in blending the bioethanol synthesized from the barley and the bio-normal butanol they synthesized from this lignocellulose biomass. I believe this was kind of the clever idea because the barley is one of the abundant the crops within the South Korea, and you can achieve this lignocellulose biomass from the mountain. I mean, South Korea is covered by the 70% of the mountain that the wood is everywhere. So our collaborator from the refinery companies and the alcohol production companies successfully synthesized the bioethanol and the bio-normal butanol with a very high purity. And my job within this project was to evaluate the combustion characteristics of the gasoline alcohol blend fuels. But the challenge of this project for me as a PhD student was the gasoline was too complex to me. Gasoline is basically multi-component fuels. It can be a mixture of more than 1,000 species. So this multi-component fuel is always challenging for theoretical studies. So I thought that this is time to use experimentations rather than using a theory or the AI technologies. So I moved on to utilizing these experimental devices called rapid compression machine. I believe many of you guys already know about these devices. For some students, I'm going to repeat I'm going to give some brief explanation about this device. The rapid compression machine is basically a device for measuring the ignition delay or the reactivity of the fuels. First of all, you have to fill the cylinder with the fuel and an air mixture. Of course, you have to vaporize the fuels. And then after a certain amount of the mixing time, you're gonna compress this fuel and air mixture adiabatically and hold the piston for a while. But after some times, you're gonna see some rise of the pressure, which indicates the auto ignitions. Let me give you one more time. Let me show you one more times. Fuel and air mixture, adiabatic compressions, and constant volume times, and you're gonna see some auto ignitions. So ignition delay is defined as a time interval between the end of compressions to the start of the auto ignitions. So by measuring this ignition delay time, you can measure the reactivity of the fuel and the air mixture, which means shorter ignition delay means higher reactivity. So as I'm working as a PhD student in the Seoul National University, I have been measuring the multiple fuels and the varying temperature, the varying pressures, the varying concentrations, for the 6 and 7 years. This is one of the examples that shows you one of the results from the rapid compression machine. This result shows you the ignition delay of the gasoline and the alcohol blend fuel with a varying temperature and the varying pressure and a varying alcohol content. The different alcohol content was indicated with the different colors. Different pressure was indicated with the different line styles. Then what we're going to do with this database? Obviously, this database is really valuable. That gives you some ideas about how the reactivity changes with the alcohol content and the temperature and pressure. But the major thing that the people want to know was how these gasoline fuels will affect the performance of the propulsion systems. So if you want to utilize this database to evaluate the performance of the propulsion system, we need one more bridge that connecting the propulsion system with the rapid compression machine. That was physics-based engine model. So in order to utilize this ignition delay database from the rapid compression machine, I had to put this database into the physics-based engine models so that I can predict the performance of the spark ignition engines with the varying engine speed and a varying engine load. The figure on the right side shows you the simulated the engine performance with the engine speed, varying engine speed and a varying engine load. When you don't blend any alcohol in the fuels, which is GEMB0 equivalent, which is pure gasoline, the maximum load of your engine is around 10 bar. However, once you blend the alcohol by the 30%, your maximum load increases by the 56%, which is very significant. And this 56% of the increase of the maximum loads means that you can downsize the engines. If you downsize the engine, you can reduce the weight of the engines, so you can make your car more efficient. At the same time, the maximum thermal efficiency of the engine increases by the 1.2% point, which is another remarkable point, because any single-digit improvement of the thermal efficiency will save a huge, significant amount of financial cost of the automotive engineering. So this is one example of how we can utilize these experimentations for evaluating the performance of the fuels in the propulsion systems. You can measure the reactivity in a fuel property in some devices like rapid compression machine. Then you can implement that database into the physics-based propulsion models, so you can evaluate the influence of the fuels on the performance of the engine and the performance of the propulsion system. So let me summarize what I've talked by far. As I mentioned earlier, my research has been about integrating the great neural networks and the theoretical combustion kinetics and the combustion experiment. And I was fortunate enough to have a balanced experience in AI and theoretical approaches and experimentations. My recent approaches has been about how to integrate these three approaches. One of the examples for integrating these three approaches was coming from by combining the theory and the GNN for improving the accuracy of the GNN model. After the couple of experience in the theoretical kinetics, I realized that the energy barriers between the OOQ, and the keto hydroperoxide is sensitive to the existence of the intramolecular hydrogen bond within the transition state. So this is exemplary, the molecular structure of the transition state, which shows you the hydrogen migration from the carbon to the oxygens. And at the same time, there's an intramolecular hydrogen bond between the hydroxyl groups and the oxygens. If you have this kind of the intramolecular hydrogen bond within the transition state, it can lower the energy barriers from the OOQ, and the keto hydroperoxides. So based on this observation from the theory, I started to implement the number of the hydrogen bonds as an input feature for the GNN models. And just by adding this input feature as an integrated neural network models, I was able to increase the accuracy of the model from the 4.29 to the 2.44. So it's almost like a double time of the accuracy. So this is why we have to have a balanced perspective in the theory and the data-driven technologies. Once you know the theory, you can make your AI model better. Another example for combining my knowledge is to combine a theory and experimental work for developing a high-fidelity combustion mechanisms. This was part of the collaborative work between the Argonne and the Sandia. And the Sandia has been the leading groups in measuring the radical concentration and the speciations from the fuel pyrolysis and the oxidations. Now, Argonne has been playing an important role for improving the theoretical accuracy of the theoretical kinetics. But as a postdoctoral researcher back then, I knew some concept and pros of the theoretical and experimental method. For example, thanks to the recent advancement of the computational chemistry, the theoretical kinetics is very accurate. But still, the accuracy of the theoretical kinetics sometimes limited for predicting the branching ratio or the kinetic rate and the pressure-dependent kinetics, because you can make your theoretical kinetics to be better in a pressure-dependent rate or the branching ratio, but you need a significant effort for making it accurate. But on the other hand, the experimental study, they are suffering from some uncertainty from the photoionization cross-section areas, but still, their experimental data is really good for constraining the branching ratio and the pressure-dependent kinetics. So based on this constant pros of each method, I was able to compensate the kinetic models, and this high-fidelity kinetic model was used for extracting the kinetic informations from the experimental data. And this is one of the success stories that I made for combining the theory and the experimentations, which shows that how this integration help us to understand the kinetic systems. So, all right. There was my introductions to my previous researches, and I prepared like 3 or 4 more slides about my ongoing researches. My previous researches was about the biofuel design, but as soon as I joined the UTEP, I realized that there's a huge opportunity in a green solid propellant. Green solid propellant refers to the solid propellant of the rocket that emits minimum toxic chemical upon the combustions. Conventional propellant emits HCl or the HCN upon the combustions, which can be toxic to the aquatic life. However, as the space mission demands increasing, the NASA and the DoD started to concern about the toxicity of the combustions from the rocket. The green propellant is the alternative of the conventional propellant that emits minimum toxic chemicals upon the combustions. So when you compare this biofuel and the green solid propellant, you will see that there's very clear similarity between them. Biofuel is liquid phase hydrocarbon that has a C and a carbon and a hydrogen and oxygens. Typically, their length is less than the C20, depending on your applications. But when you look at this green solid propellant, it is a mixture of the oxidizer and a metal and a polymeric binders. I was particularly interested in these polymeric binders because these polymeric binders has a very similar molecular structure with the biofuels. But the only difference is that this polymeric binder is solid phase and the biofuel is liquid phase. So I thought that there must be something that I can do for developing a novel polymeric binder for the green solid propellant based on my expertise in the biofuel design. So this was my ongoing researches that I was doing within my teams in the UTEPs, which utilized the AI technology for designing a polymeric binder for the novel green solid propellant. I did the exactly same thing that I'd done in a biofuel design. I screened out the polymer based on, I screened out the 16,000 polymers based on their pyrolysis characteristics like a char yield and decomposition temperatures. And then I did a second screening process based on their mechanical properties like a tensile strength at the yields, tensile strength at the break. Obviously, you want to have a polymer with a higher mechanical strength because the mechanical strength of the polymer is important for the integrity of the structure, the rocket structures. Once you find out this polymer with a higher mechanical strength, I did an additional screening process based on the ecotoxicity of the polymers. After all this screening process, I was able to recognize only 3 of the polymers satisfied all the stringent regulations on the ecotoxicity and the mechanical properties and the pyrolysis characteristics. And these 3 polymers are the one that satisfies everything. And now I'm in the process of manufacturing the miniature, the solid propellants, so I can demonstrate this feasibility of the AI-based polymer design. And now I'm collaborating with the 3D printing guys within my department. So this work was conducted by my clever research assistant like Renee Hesses and Victor and Emilio and Sooting. This work will be presented on a U.S. National Combustion meeting on March at the energetic material combustion sessions. Another initiative that I'm having is to utilize my theoretical capability for improving the polymers that is being used for the aerospace applications. Especially, I'm interested in polycarbonylate. Polycarbonylate is polymer that has a silicon and a carbon in the backbone in the alternating metals. One of the beauty of this polycarbonylate is it's polymer, but when it burns, it makes beta silicon carbide. So beta silicon carbide is a ceramic, but the SMP10 is polycarbonylate is polymers. Usually, it is comparatively harder to synthesize and fabricating the ceramic part, but the beauty of this polycarbonylate is you can start from the polymers, then you can use this polymer for the 3D printing the part. Once you fabricate the very complicated geometry with this polymer, you can put it into the oven to make a complicated geometry ceramics. So this beauty of the polymer to the ceramic conversion process has been really popular choices for the 3D printing engineers, but obviously there was some challenges in utilizing this polycarbonylate. That is, this is pictures from one of my colleagues in the UTEP. He tried to put these polymers into the oven. He found out that there's a lot of porosity inside of the sample. Actually, this porosity is coming from the bubble, and the bubble is coming from the gaseous product from the pyrolysis. Even though this bubble is coming from the gaseous product, there's a very limited understanding how this gaseous product is being produced from the polymers of the polycarboxylates. So I thought that this is the right place for me to utilize my theoretical capabilities. So I did a molecular dynamic simulations of the polymers, and you can see that at the moment, as soon as you pyrolyze these polymers, this polymer dissociates fastly and start to form some particle like this. Can you see this particle? This particle is precursor of the beta silicon carbide. So by using these molecular dynamic simulations, we are able to see some we are able to get some mechanistic understanding of how this polymer is being converted into the silicon carbide. And we are trying to convert this molecular dynamic simulations using a density functional theory, so we can construct the kinetic model that simulate the polycarbonate conversions to the silicon carbide. This work was done by my the research assistant like MD Rajals and Hasses and Renee and Ivan. This probably the last slides that I prepared. At the same time, I'm pushing myself to develop some experimental devices for measuring that the pyrolysis product from the polymers. Pyrolysis product, the polymers. This is a schematic diagram that I was developing. Are we gonna pyrolyze this polymer using a pyroprop? And then this gaseous product from the pyroprop will be pushed to the flow reactor, so we can measure the pyrolysis of this gas-phase product. And the pyrolysis of the gas-phase product will be measured through the gas chromatography and oxygen sensors. Currently, I'm setting up and purchasing all the devices that I have to buy for constructing this the polymer pyrolysis studies. Is actively being constructed by the research assistants like Fahim, Renee, and Hasses. All right, I have to mention about this effort in the UTEP. Right. So I was fortunate enough to be a faculty advisor of the UTEP rocket team. My experience in the polymer design and the combustion has been playing a crucial role for helping the students to construct their own solid rocket. This is video from the last competition at the Spaceport America Cups. We are very successful in securing the 4th place out of the 20th university across the world. So this video is beautiful. So I wanted to mention that our researches in the combustions in a solid propellant can eventually help to foster the future engineers and scientists within the regions in Americas and across the nations. Right. I want to thanks to all the funding agency that supported my researches, including the UT system, the UTEP, the DOE, and the ExxonMobil, and the COPTMA, and all the collaborators like Yale University, and the CSU, and Sandia, Oregon, and the NRELS, and some the Korean entities like Hyundai Steels and GS Caltex, and a Modi and a Seoul National University. And this is team of my UTEP groups, and our laboratory is called the Sustainable Propulsions and Reaction Kinetic, which is called SPARK Laboratory. We already have a kind of significant amount of members. All of them are collaborating each other and contributing to the scientific progress. Thank you for your attention, and let me know if you have any questions.
Thank you. Thank you very much for this very interesting talk. Like you said, it's now you are awaiting some questions, so this is the time for the audience. If anyone in the audience wants to ask any question, please feel free to unmute yourself and ask a question. If there are no questions, then I would like to ask one, or maybe two. The first one is related to the fact that is related to the uncertainty in the composition of these biofuels in the end. I'm guessing that in the end, what we produce, we don't know if it's going to be used for industrial or transportation in a real engine. We don't really know the exact composition of the fuel. So have you thought about investigating that, doing some uncertainty propagation of the different fuel properties that real SAF could have, or this GNN can be somehow extended in like Bayesian GNN, something like this?
It is. that's really clever and important questions. First of all, when it comes to the difference between the real application and a pure design is coming from the multi-components. For example, I mean, when we are designing a biofuel, we assume that this fuel will be used as a single component, but actually, of course, it never been used as a single component. It always being mixed with let me see. Let me pause here. Here, sorry. Of course, this fuel will be used as multi-component. It will be blended into the multi-components. So recently, we had some publication in the Society of the Automobile Engineering, so we can extend our GNM model to cover the multi-component fuels. So we obviously know that there's some flaws of assuming the fuels as a single component fuels, but the research groups at the Colorado State University has developed the nice methodologies for implementing the model to be a model to cover the multi-component fuel layers. And that's the one thing that we are doing right now. So expanding the model to cover the multi-component fuels. On the other hand, as you mentioned earlier, there's some uncertainty in the database. It is always problematic, and it is pretty hard to understand the propagation of the errors from the database to the predictions. The only thing that we are doing right now is to accounting for the reliability of the database by putting a different weighting on the different weighting depending on the source of the database. There's many ongoing researches on implementing the Bayesian approaches for improving the GNM models that consider the uncertainty of the database, and they can be one of the future directions that we can go for implementing these technologies for the real applications.
Okay, thank you. If no one from the audience would like to ask any other question, I have another one more related to the graph neural network. I'm curious about this algorithm. I was wondering, because I saw in your slide you mentioned feature swapping and some sort of this. I'm wondering, do you use just GNN to like relate a certain molecular structure to a certain fuel properties, or you could use this also to kind of optimize the molecular structure, so to get a certain value of a fuel property?
Again, I was just laughing because it was very clever questions. I mean, of course, one of the limitation of this GNN model is single directions. You have to have a molecular structures to predict the fears. But of course, but there's a lot of people who are interested in to do this GNN model in the opposite directions. Like once you have a field property, they want to get a novel molecular structure that satisfy their field properties. So that is usually what the peoples are doing for making this GNN model to be opposite direction is to they are using the generative AI, which is called the generative adversarial networks. There's also a few success story for utilizing this generative AI for the developing a novel molecular structures in the opposite directions. They were successful in the drug design and some polymer design back then, but there has been no study by far for utilizing the generative AI for designing a novel fuel yet. So I think that is the future direction that we have to go. Actually, I'm doing some researches on it. You're right on.
Good, thanks. And yeah, if there are no other questions from the audience, then I think it's time I think we can conclude this Q&A session. And I would like to thank you again, Jaeyoung, for this very interesting talk and this Q&A sessions, and for having accepted our invitation. And I wish you, well, a nice day and a nice weekend too. And I wish also everyone a nice weekend, and we'll see everyone at the next appointment of this lecture series. Thank you.